Mayday Helicopter Stories. Our mission is improve aeronautical safety in order to identify latent failures and effective monitoring of risk mitigation for the prevention of accidents, as well as expanding the knowledge of flight and maintenance personnel by announcing previous events. Loss of tail rotor effectivines. On February 10, 2018, about 17:19 Mountain Standard Time, MST, an Airbus Helicopters EC-130B4 helicopter, N-155GC, was destroyed when it was involved in an accident near Peach Springs, Arizona. The pilot and one passenger sustained serious injuries, and 5 passengers were fatally injured. The helicopter was operated as a air tour flight. On the day of the accident, the pilot performed a canyon landing and an air tour flight before the accident flight. All of the day's flights departed Boulder City Municipal Airport, BVU, Boulder City, Nevada. Both the second flight and the accident flight had a destination of Quartermaster, an unimproved landing site regularly used by the operator within the Grand Canyon's Quartermaster Canyon. The pilot's second flight of the day took place in the early afternoon and returned at 14:55. The accident flight departed at 16:42. The accident helicopter reached the Hoover Dam about 16:52 and entered the Grand Canyon West Special Flight Rules Area 50-2 about 17:13, where the pilot flew the standard helicopter route known as the Green 4 route. The last radar return was captured at 17:17 and depicted the helicopter about 3.5 nautical miles, (nm), west of the accident site, consistent with a descent into the canyon to Quartermaster. The accident helicopter was one of 10 helicopters scheduled to land at the site on the afternoon of the accident. The tour operation intended for the 10 helicopters to sequentially land at Quartermaster and allowed for them all to be present at the landing site at the same time. The accident pilot stated that, during the approach to Quartermaster, he noted that the 8 helicopters that had already landed were facing in different directions, indicating variable wind conditions. The combination of the windsock direction, orientations of the parked helicopters, and unoccupied landing pads on the west side of the landing area prompted the pilot to conduct an approach from the west and touch down on one of the west landing pads. He recalled that the 2 helicopters that landed immediately before him were on the west landing pads facing east, the same as his chosen approach direction, and noted that the windsock indicated wind from the north/northeast. The pilot stated that he normally remained on the north side of the Colorado River, crossing the river between 200 and 300 feet above ground level, AGL, while approaching Quartermaster for landing. After crossing the river, he entered a left-turning descent toward the landing area. He stated that, as he made the left turn, the helicopter encountered what he described as a violent gust of wind and began to spin, and as a result he was unable to maintain directional control. A Papillon pilot on the ground at Quartermaster watched the accident helicopter as it approached from across the river and assumed that the pilot planned to land on the west pads based on his approach path. He reported that the helicopter decelerated and then entered an approximate 15 degrees nose-up pitch attitude. While maintaining altitude, the helicopter began a left turn toward the landing site. According to the witness, during the turn, the helicopter transitioned into a level attitude, followed by a nose-low attitude. He further reported that the helicopter began to drift aft as the left turn continued and returned to a level attitude before it rotated 360 degrees and began a descent. After a second 360 degrees rotation, the helicopter collided with terrain. A post-impact fire ensued. Previous approach and landings at Quartermaster. The first 5 helicopters to land at Quartermaster on the afternoon of the accident approached from the east and landed on the east pads, facing west. The next 3 helicopters landed on the west pads and used a similar approach as the accident helicopter. The 10th helicopter did not land due to the accident. The pilot began his employment as a full-time pilot with Papillon Airways on June 3, 2013 and was trained by Papillon in the accident helicopter make and model. In 2014, the pilot transitioned into a role as a part-time pilot to pursue another career opportunity. At the time of the accident, the pilot's primary occupation was in a different field, not as a pilot, but he continued flying for Papillon in a part-time capacity. Company training records revealed that the pilot's most recent line check in accordance with 14 CFR Part 135 was accomplished in December 2017 and showed satisfactory grades for all areas of the examination. However, the lead pilot who conducted a portion of the pilot's training in preparation for this line check reported that he had marked the pilot's performance unsatisfactory. Specifically, he noted that the pilot had experienced difficulty maneuvering the helicopter during high wind conditions and did not have enough altitude as he turned during 180 degrees autorotations. The pilot passed his check ride with another lead pilot 1 to 2 days later. According to the operator, at the time of the accident, the pilot had flown passengers into the Grand Canyon for them a total of 836 times, with 581 landings at quartermaster. The pilot stated that he felt comfortable flying the Airbus helicopters, formerly Eurocopter, EC-130B4 helicopter and landing at quartermaster. Prior to becoming an air tour pilot for Papillon, the pilot flew air tours in non-turbine-powered helicopters in the Midwestern United States. Loss of tail rotor effectiveness. LTE is a critical, low-speed aerodynamic flight characteristic which can result in an uncommanded rapid yaw rate, which does not subside of its own accord and, if not corrected, can result in a loss of aircraft control. Information on this subject has been published by many organizations including the FAA and helicopter manufacturers. The FAA Helicopter Flying Handbook, FAA H8083-21B, contains an in-depth discussion on LTE. Chapter 7, Helicopter Performance, addresses helicopters with main rotors that rotate counterclockwise, and states, the wind direction is also an important consideration. Headwinds are the most desirable as they contribute to the greatest increase in performance. Strong crosswinds and tailwind may require the use of more tail rotor thrust to maintain directional control. This increased tail rotor thrust absorbs power from the engine, which means there is less power available to the main rotor for the production of lift. Some helicopters even have a critical wind azimuth or maximum safe relative wind chart. Operating the helicopter beyond these limits could cause a loss of tail rotor effectiveness. Chapter 11, Helicopter Emergencies and Hazards, defines LTE as a condition that occurs when the flow of air through a tail rotor is altered in some way, by altering the angle or speed at which the air passes through the rotating blades of the tail rotor disc. It further states, the main factors contributing to LTE are 1. Airflow and downdraft generated by the main rotor blades interfering with the airflow entering the tail rotor assembly. 2. Main blade vortices developed at the main blade tips entering the tail rotor disc. 3. Turbulence and other natural phenomena affecting the airflow surrounding the tail rotor. 4. A high power setting, hence large main rotor blade pitch angle, induces considerable main rotor downwash and hence more turbulence than when the helicopter is in a low power condition. 5. A slow forward airspeed, typically at speeds where translational lift and translational thrust are in the process of change and airflow around the tail rotor will vary in direction and speed. 6. The airflow relative to the helicopter, a worst case, relative wind within plus or minus 15 degrees of the 10 o'clock position, generating vortices that can blow directly into the tail rotor. This is dictated by the characteristics of the helicopter's aerodynamics of tail boom position, tail rotor size and position relative to the main rotor and vertical stabilizer size and shape. B. Weathercock stability, tailwinds from 120 degrees to 240 degrees, such as left crosswinds, causing high pilot workload. C. Tail rotor vortex ring state, 210 degrees to 330 degrees. Winds within this region will result in the development of the vortex ring state of the tail rotor. 7. Combinations of A, B, C of these factors in a particular situation can easily require more anti-torque than the helicopter can generate, and in a particular environment LTE can be the result. There are a number of contributing factors, but what is more important in preventing LTE is to note them, and then to associate them with situations that should be avoided. Whenever possible, pilots should learn to avoid the following combinations. 1. Low and slow out-of-ground effect. 2. Winds from plus or minus 15 degrees of the 10 o'clock position and probably on around to 5 o'clock position. 3. Tailwinds that may alter the onset of translational lift and trans.